Hi, welcome back. A lot of beginning astrophotographers want to know if photos of the night sky are real. What does that mean? I think that is a loaded question. So in this video, let's narrow the question. If we can prove that part of something is fake, does that mean it all is? And what if, going down the rabbit hole, we find out that all photography is fake? And your vision is fake. Yeah, I bet you didn't think I was going there. Welcome to Deep Sky Detail. Alright, let's return to the big question for a second. Is astrophotography fake? I don't think we can answer this big question without breaking it down a bit. This is going to take quite a few videos to cover completely. So let's start smaller. Let's focus today's video only on color. And this will be only the first video on color. So is color in astrophotography fake? Well, there's a simple way to answer this, and here it is. Color itself is fake. Because it is fake everywhere, even in astro photos. Therefore, color in astrophotography is fake. Thanks for watching. Okay. Don't hit the dislike button yet, please. I'll explain. Right now, you're probably telling yourself, color is just a representation of different wavelengths that your brain interprets. To that, I'd say, yeah, you're kind of mostly right. But it's the kind of mostly where all the interesting cognitive science is. What we're going to do is work from the bottom up, from cells to perception. Today we'll focus on cells and get into perception, and as we do, I think you'll see that what starts out as mostly a measurement of photons becomes something so much more complicated. It can also free up rigid thinking about what astrophotography should or shouldn't be. Alright, let's start with the retina behind your eyeballs. Most of you have probably heard of the two types of photoreceptors, rods and cones, where the cones are responsible for color vision and rods act as general light receptors. This is for the most part true, but it can lead people to think that rods give you information about how bright something is, which is not entirely true. In reality, rods generally play a role in vision when it's dark. When it's bright, the cones, which people normally associate with only color vision, also tell you how bright things are. The rods are basically turned off. Light is light regardless of color. And your brain can get all the information it needs about brightness from the cones alone if there is enough light. For those of us who love visual astronomy, this is why it takes so long to get dark adapted. Your rods need time to turn on when it gets dark. Okay, let's focus on cones, since we are, after all, talking about color vision. Without them, we wouldn't see colors. Interestingly, without at least two different types of cones, we couldn't see color. Why, you might ask? Well, let's think about it for a second. Let's say we only had one color receptor cone. When light hits the cone, it sends a signal to your brain. But how could it tell the difference between red and blue light? Well, you might say that if blue light hits the cone, then it sends 5 signals per second. And that if a red light or red photon hits it, it sends 10 signals per second. Would that work? Well, it kind of sounds reasonable. But it wouldn't work. Remember that cones tell us information about brightness too. Let's say that in 1 second, this super cone sends your brain 10 signals. How would it know if it's receiving 5 photons of red light or 10 photons of blue light? It can't. The intensity signal is muddled with the color signal. You need more than one type of cone so that you can compare between the two colors, and the number of cones an animal has will influence the number of colors that it can see. In general, for humans, but not always, we have 3 types of cones. You may have heard that there are cones associated with red, green, and blue light, or R, G, and B cones, respectively. Personally, I don't like this terminology. That's because when you look at the colors each type of cone is most sensitive to, it doesn't always line up with RGB. You could also describe them as yellowish green, greenish yellow, and blue purples. Plus, There can be variation among people's cones, so some researchers will say the three types are distinguished by the frequency of light it's most sensitive to: long, medium, or short, or L, M, and S. But let's stick to RGB. I'm not that concerned about the terminology, and calling them RG or B cones is useful because it's easy to remember and apply to my examples. Alright, so let's just do a little demonstration here. I think we've got all the information to talk about the trichromatic theory of color vision, which is kind of nice, right? So we have tri meaning three, chromatic meaning color, and theory. Seems pretty easy, right? So let's just, do a little demonstration in GIMP. I've got the Flaming Star Nebula here that you can see. And let's just go into the red channel and we can kind of demonstrate that, like, you see more red because you have more red colors hitting the cones in your brain, sending a signal, right? And we can reset that. Same thing with green. We could increase the brightness of the green and you would see more green. I mean, it's fairly straightforward. We want to see more blue, we just increase the brightness of the blue. Makes sense. What about yellow? How do we get yellow? Or purple or magenta, right? How do we get all these other colors like orange? So clearly we're missing something. The next super important concept is something called color opponency, or opponent process theory. Basically, the idea is that your brain is constantly comparing the input it receives from your cones, and it does so in a systematic way using two main color channels. And that's where levers come in. Levers are fun. We put them in kids' playgrounds. Did you ever play on the playground with a lever? I called them seesaws. You might call them teeter-totters. Good times. Good times. What's fun about levers is that if you push down on one side, the other side gets pushed up. One side is down, the other is up. One side is up, the other is down. It's simple. And it's exactly like color vision. Well, sort of. Each channel is like a lever. On the sides of the lever are some combination of cones. When one side is active, in this representation the lever is up, it deactivates the other side, meaning it pushes it down. It's generally thought that humans have two main channels. The first channel is the red-green channel. On one side are your R cones, and on the other side are your G cones. If a lot of your R cones are active, it pushes down the signal of the green cones. So if you see something as red, a lot of your R cones are detecting photons from an object relative to the G cones. How red something is can be thought of as a formula where the color of red or green equals the activation of your red cones minus the activation of your G cones. Now, I mentioned that there are at least two main channels. The other channel is the yellow-blue channel. On one side of this lever are your red and green cones, and on the other side is your blue cones. The formula for this would be the color of yellow or blue equals the activation of your red and green cones minus the blue cones. What's really interesting is that we can see this in how our cones are wired in your retina itself. The top layer of your retina consists of rods and cones. Underneath that are supporting cells. These are horizontal cells, bipolar cells, ganglion cells, amacrine cells, etc. Kind of reminds you of an artificial neural network, doesn't it? Except it's a real neural network. Well, anyway, these supporting cells are really important for interpreting the signal the rods and cones are receiving. The R and G cones can connect to the same bipolar cells to send information to the brain. Blue cones, however, only connect to one type of bipolar cell. You can see that the B signal from the B cones is entirely separate from the R and G cones. The opponent system starts to manifest itself in the retina itself. Okay, so there are four basic colors in two pairs, red and green as one pair and yellow and blue as the other pair. Red and green oppose each other. Yellow and blue oppose each other. All other colors that we see depend on the combination of these two opponent pairs. If there is no signal going to the B cones, a lot of signal going to G cones, and even more signal going to the R cones, you'll see orange. We can show that in these levers. Here on the YB lever, blue is down and yellow is up. On the RG lever, R is up compared to G. The resulting color is orange. Remember how unbalanced a lever is depends on the relative difference of the signal on each side. Even though G cones are receiving signal, The G side is still deactivated on the RG channel because there is more R cone signal. It also means that some colors should be impossible to see, like reddish green. Let's do an experiment real quick. All right, so I'm back here in GIMP. I've got a really special treat for y'all. This is something I discovered, in my backyard. It's a picture of the Great Banana Nebula, right? It's a starless image. I had to brighten up the image pretty well so you could see, But the banana yellow is a rare sodium nebula that gives off yellow light, right? I've run this through StarNet++, so there are no stars in it. And this is a combined RGB image. I'm going to deactivate this out here just so we have the nebula by itself. And below it, we have, just the red channel. Okay, so this is just a red channel that I've colorized to be red so it looks red. Now, if we reactivate the full RGB image, we've got the yellow on top and the red on the bottom. If I start to make the yellow channel image transparent, some of the red colorized image will start to peek through. So let's go ahead and do that for a second. Your brain's yellow-blue lever kind of remains unchanged. There's still no blue light sending signal to your eyes, but the red-green level is going to change, and you'll see this here. So the red-green level is going to change, and what's going to happen is, probably as you expected, the banana nebula is going to get a little bit more orange as we remove more and more of this yellow. The red-green level is unbalanced, and you interpret this as orange, right? That's pretty cool. Now let's try one more example. So every couple of months, something rare happens to the Great Banana Nebula. The sodium ions mysteriously dim, and suddenly cobalt ions begin to radiate light for some unknown reason, probably aliens. The answer, at least in the US Congress lately, has been aliens.
You said that the government has alien bodies or alien species. Have you seen any of the bodies? That's something I've not witnessed myself.
So let's go with that, aliens. Luckily, I got an image of it as it was dimming and as it was fully blue. So my question to you is, if we fully reactivate this yellow layer, what do you think is going to happen at the transition when the sodium and cobalt ions are emitting roughly equal amounts of light? Well, before you saw this video, your intuition might say green. Green is, after all, kind of the mix between yellow and blue. Well, my intuition tells me that intuition is usually wrong about half the time. Your intuition would be correct when we were creating orange, but the true answer when there are equal amounts of yellow and blue light is that the colors will cancel out. The blue cancels or inhibits the yellow, it becomes gray or white or whatever. So let me show you. So here we are. Here's the banana. Let's go ahead and artificially dim this for a second, and what you'll see is that the image gets gray. It doesn't get green. It gets gray, and once enough of the blue light, once enough of the yellow light is gone, it'll slowly transition to blue. This should be the death knell for the idea that color represents something objective in the real world. When you see something that is red, there might also be yellow and blue light hitting your eyes, but because they cancel out, you only see the red. Or when you see yellow, it could be yellow light you're seeing, but it could also be a combination of red and green light. Remember what I said earlier in the video? Let's say we only had one color receptor cone. When light hits the cone, it sends a signal to your brain. But how could it tell the difference between red and blue light? Well, you might say that if blue light hits the cone, then it sends 5 signals per second. And then if a red light or red photon hits it, it sends 10 signals per second. Would that work? Well, it kind of sounds reasonable, but it wouldn't work. Remember that cones tell us information about brightness too. Let's say that in 1 second, this supercone sends your brain 10 signals. How would it know if it's receiving 5 photons of red light or 10 photons of blue light? It can't. The intensity signal is muddled with the color signal. But with 3 cones, we still don't have a solution for the fact that the intensity signal is muddled with the color signal. Things are just more complex. Our brain still cannot tell the difference between intensity and wavelength in many situations. We could be seeing 5 photons of red and 5 photons of green, or we could be seeing 10 photons of yellow. Color is an object that our brain creates. So it's fake, right? Well, kind of. Color still tells us useful information about the world. It's not perfect. It's a model the brain creates to help us make sense of the world. And no model is perfect, but some are useful. And color is useful. And pretty too. Now back to astro images. Color is, I think, a fairly subjective thing. If subjective means fake, then color in astrophotography is fake. But it also means that all of photography is fake, and it means that our color vision is fake. And maybe, possibly even our vision is fake. But it's even more fake than you might realize, because color is even more subjective than what we've covered here. But don't let this knowledge disappoint you. Let it empower you. When you process your images, make the colors whatever you want. Increase the saturation if you'd like. Color may be subjective, it may be fake, but it is useful, and it does make astrophotography a lot more interesting. So the next time someone criticizes your astrophotos for being the wrong color, or being too saturated with color or whatever, show them this video. Make sure that they know that color is literally and figuratively in the eye of the beholder. We've really only scratched the surface of color. There's so much more. Like, how do contextual cues affect color perception? Here's a spoiler. Context is a huge deal in color perception. Because we don't live in a nebula and are unfamiliar with its context, would we be even able to comprehend the color we see if we could see it? Well, that's a topic for another video. If you enjoyed this video and want to see the next part in this series about color, make sure you're subscribed and like the video so that I know it's something you want to see. I hope you learned something interesting. Thanks for watching.